Well, we use the word in reference to the laws of physics that apply in the microscopic world at the level of individual atoms, individual electrons, elementary particles, where physics is qualitatively different than what we experience in our everyday lives. You ever been to the beach? You see waves coming in. Why do the waves have characteristics? Speed. That's all classical physics. Send a rocket to the moon. There's no quantum physics in that.
We're discussing right now quantum world, which is at the very smallest scales. The elements of reality down at that level are not described by what we're used to, which is the momentum of something or the position. If you were to go and ask the same question at the microscopic level, at the quantum level, then things break down. So things are different there.
It's called the Heisenberg microscope. If you imagine if you have a little particle and you wanted to look at it, you could know its position perfectly well at one instant in time, but then you wouldn't know where its position was after that, right? So even light that you'd use to observe it would still disturb it. It would transfer momentum to the object and kick it. And now all of a sudden you've given it an infinite uncertainty in terms of its velocity. To predict where it is after that, you'd have infinite uncertainty in terms of its position. What makes quantum mechanics sort of fascinating, and so this idea that an object can't both have its position well-defined and its momentum well-defined is, at the same time, it's fundamentally just a property of waves, just a mathematical property of wave equation. So imagine a water wave. If I wanted to have a localized little sample volume of water, and then I asked what does it do after? Well, it's going to disperse very quickly. Whereas if I have a sinusoidally traveling water wave, it's going to be dispersed over a huge range of space, but it has a very well-defined momentum. And that has nothing to do with, that's just classical physics, just the physics of waves. We're trying to understand these wave properties of things, you know, the wave property of you and I. We don't disperse, electrons don't just fall apart, protons just fall apart. It's natural to think of them as point particles or little objects. It's not natural to think of them as waves. But that's what part of what quantum mechanics is doing. The whole point is that people are now exploring bigger quantum objects that are much larger, you know, billions of atoms in it, in our case. And the question would be, does it still behave quantum mechanically? Can I describe that with a wave function?